Part A asks you to determine the value of k. So k is this unknown constant here. We are told that this curve here of this parabolic gateway arch has an equation in the form of this. So it's a quadratic, and the variable is x, but we don't know this constant k. So in part A, we need to find out this constant k. Now we do know that this curve here passes through a couple of points that we do know the coordinates of. So for example, it passes through the origin, which is 0, 0. We also know that it passes through point N, and that point N would have an x value of 12 and a y value of 0 because it's on the x-axis. And we actually also know point M, capital M, the turning point, because it's a parabola, which means it's symmetrical left and right of the axis of symmetry. And if we know that the total width is 12, half of that will be 6. So this coordinate here will actually have an x value of 6, and it has a total height of 8. So we do know 3 coordinates that it passes through. I'm just going to use the origin because it's just easier just with zeros to find out this k value. So you could sub in potentially any 3 of these coordinates to find the value of k. I'm just going to choose the origin here. So I can substitute in a coordinate that the curve passes through, which I'm going to use as the origin, 0, 0, and then rearrange and solve for k. So I put in so this is my x value, this is my y value. I'm going to sub my x value into here, my y value into here, and then that'll just leave me one unknown k, and I can solve for k. So this first step here is the substitution step. Now just be careful here, this bracket doesn't cancel to 0 because I'm left with 0 subtract 6 all squared. So this actually simplifies down to negative 6 squared. Now negative 6 squared is equal to 36, which is why now I have k times 36, which I can write as 36k. The left-hand side is still 0, and then I have this constant plus 8. From here, I'm going to subtract both sides by 8. So in other words, I now have negative 8 is equal to 36k. And then I can just divide both sides by 36, and I will get, let's just check that on the calculator. So negative 8 divided by 36 is negative 219. So that right there is the value of k, which means this equation here, I could actually potentially I could rewrite it as y is equal to negative 219, x subtract 6 all squared, plus 8. Okay, that is part A. Part B asks you to write down an integral that represents the cross-sectional area under the arch shown as OMN. So from O through M down to N. So basically, this is asking for an integral that represents this shaded region here, the area under the curve, which is also the cross-sectional area underneath this gateway arch. Okay, so area under curve between a lower boundary of the origin and an upper boundary of point N. We do know that the origin has a x value of 0, and point N has an x value of 12. So our boundaries for our definite integral, so we have a definite integral here with a lower boundary of 0 and an upper boundary of 12. And we want to find the area under the curve, and we now know the equation of this curve, because in part A we found the value of k, which was negative 219. So this is the definite integral here. This is the answer to part B, and let's just read it out what it means. It means the area under the curve bounded by the x-axis is equal to the definite integral with a lower boundary of 0, an upper boundary of 12, so in other words, from 0 to 12, of the equation of the curve, which is this term, this expression here, and we're going to integrate it with respect to x, which is why we see this dx here. Okay, that is part B. Part C asks you to find the cross-sectional area under the arch. So in other words, we need to evaluate the definite integral that we found in part B, which is finding the area underneath this curve and bounded by the x-axis. So simply put, we need to find out what this definite integral is equal to. Now you can do this in 3 different ways. 2 of them using your calculator, one just in the normal calculator screen, one in the graphing section. I'm about to show both. And then the third way is to actually do it by hand, which is what I've shown here. And I'll show that at the end of this video. So first things first, let's find the let's find the value of this definite integral in the main section of the calculator. So to do that, we go Menu, Calculus, Numerical Integral, and let's actually type in this definite integral. So a lower boundary of 0, an upper boundary of 12, and the equation of the curve that we are finding the area underneath is negative 2 on 9, brackets x subtract 6, all squared, plus 8, and we are integrating with respect to x, so dx, hit enter, and we get 64. So that's our first answer. Very easy. If you're confident using your calculator, fantastic. Let's actually do it in the graphing section now. So I'm actually going to enter this equation here. I'm actually going to plot it on the graph. So this is negative 2 on 9, x subtract 6, all squared, plus 8. Now I may need to adjust my zoom setting shortly. Let's just do that. Menu, zoom out. And let's put the zoom box around the area that we're interested in. So zoom box. Doesn't need to be too precise here. Okay, so there we have there. Now let's go ahead and find the area under the curve between a lower boundary of 0 and an upper boundary of 12. To do that, we go Menu, Analyze. Number 6, Integral. Now it asks for the lower bound. I tend to just type it into my calculator, not try and put my cursor on it, because I often can't do that very accurately. So I'm just going to enter 0. And then the upper boundary, again, I'm just going to enter 12. And there we have it. There's our second answer, 64. So the area under the curve is 64. Now the units here are in meters, so the units are going to be meters squared. So there are 2 calculator approaches to finding this area. Now finally, let's talk about doing it by hand. I think it is important to be able to do it by hand. It's also interesting to understand the integration process. And there's kind of 2 main steps to it. And the steps are, we need to understand how to anti-differentiate. So we have this particular curve here, and in order to find the area under the curve, we need to anti-differentiate the equation to find its antiderivative, and then we use the fundamental theorem of calculus to actually find the area between the 2 boundaries. So let's just talk this through. Okay, so in this first line here, I've just simply rewritten the definite integral. In this next line here, I've expanded out my x subtract 6 all squared term. So you could do this by hand. That'll become x subtract 6, and then you could use FOIL to find out what that is equal to, that expansion, and that's what it's inside this bracket here. In the next line, I have then multiplied through this negative 2 on 9, so distributed that through all the terms in the bracket. So now that gets me to this line here. To go from this line to the next line, I've grouped like terms. So this negative 8 with the positive 8 becomes 0. The first 2 terms remain the same. Okay, to go from this step to this step, this is where the anti-differentiation process occurs. So let's just recap how to do this. If I have a term ax to the b, where a is my coefficient, so for example, negative 2 or 9, and b is my power, for example, 2. If I go to then anti-differentiate, I raise the power by 1, and divide by that new power. So looking here, I've raised the power by 1 and divide by the new power. I tend to write the fractions out the front and just anti-differentiate the x term, and then the next line after that, I'll just clean it up and multiply them together. That's how I prefer to do it. I've done the same thing for the second term here. So I currently have a power of 1 on my x term. I go to anti-differentiate, I raise the power, 1 becomes 2, and divide by that new power. Now, when we go and do the anti-differentiation step, we move the boundaries, the lower boundary and the upper boundary, in these positions here on the square bracket. So lower boundary is positioned here and upper boundary is positioned here. Okay, in the next step, I have just cleaned up. So negative 2 on 9 multiplied by 1 on 3 gets negative 2 on 27. And in the second term here, the 8 on 3 multiplied by the half gets 4 on 3. And I still have my boundaries here. Now, to go from this step to this step, this is where the fundamental theorem of calculus comes in. Now, this is all about how do you find the area bounded by a curve and an axis. In our case, the curve and the x-axis. So we have a definite integral, as we have written here. The fundamental theorem of calculus tells us that this area is equal to the antiderivatives. We substitute in the upper boundary and we subtract the antiderivative substituting in the lower boundary. So here, this here is our antiderivative. In order to find the area of this definite integral, we sub in the upper boundary of 12, subtract, and then we sub in the lower boundary of 0. And this is pretty complicated here, although these two terms here will cancel because they're multiplied by 0. But from here, I'd recommend just using your calculator and then finding out what this is equal to, and that comes out as 64. So that is part C, and that is the area under this gateway arch.